Okay, so thank you, organizer, for giving me this opportunity. So today I'm going to talk about the power spectrum measurement from the disk scan observations, mainly from the MWA. So these are my collaborators, and some of the collaborators are present here. Okay, so what the disk scan? Disk scan is basically a telescope pointing toward the zenith and sky is passing through. You can think of it in opposite ways, that sky is fixed and telescope is moving, and you can point different part of the sky at different times. So this is the primary beam of the sky, and different points here are the different point at different time, and the telescope is responsive. Okay, so in the disk scan, what our idea is that we can focus on some part of the sky, let's say here, and combine all the measurement from different pointings to get the final power spectrum or the final fluctuations at some part of the sky here. So that is the idea we are trying to do here in the drift scan observations. What is the advantage of that? I can change our parameter. So basically, this is the window function. I apply a window function in the sky, interested in that part of the sky. Even the drift sky is moving, but we are still restrict to that part using a fixed window and change the pointing center at different time. So what is the advantage? I can choose different window function, different distance to get the independent measurement of sky and then combine all of them to increase the signal to noise ratio. So that is the drift scan observations, and our aim is to develop an estimator from the drift scan observations to combine the different part of the sky signal to increase the signal to noise ratio, and that's we called as a tracking trapper guided estimator. So in mathematical formalism, how we have done. So this is the window function, the W, that is basically the restrictions of the sky. And this phase factor, I know what point I am interested, and I know which point the telescope is pointing. So using proper phase factor, I can combine all of the measurement and add them up to increase the signal to noise ratio. And this is the mathematical estimator. So we combine all the visibility and do the self correlations. Finally, it will give the power spectrum. So that is the idea. And we took the MW observations for this measurement. And this is the drift scan observation. This is the starting point. So the RS start from minus 349 to 70 degree and with 0.5 interval. And total hour of observation is 5 hours 24 minutes. And we combine the 10 nights of data. Individual nights we analyze separately, and then we combine. And final data is have 5 hours 20 minutes. But what are the so in that observation, so that is the sky coverage. And in terms of the parameters, so this is the frequency band, 30 megahertz bandwidth, and this is the center frequency. And one of the MWA problem is that it is a periodic flagging pattern. So each of these bandwidth is divided into 24 coarse band containing 32 channels. And each of the sub bands, there are 4 channels flagged in the both side and one center channel. So basically there's a periodic flagging pattern at each sub band. And this is the UV distributions of the phase 2 configuration of the MWA. And the baseline is larger than the 200, but their density is very less. So we are concentrating only on the center part, that is the plus minus 200. And this is the baseline density. So what happens due to this channel flagging at the first 4, last 4 in the center of each subband? If you do the Fourier transform and we can measure the power spectrum, definitely this we will get without any corrections. So this power spectrum is basically we are expecting, and then we do the flagging. This is some simulation study. So we have to get rid of this flagging pattern in the channel so that we can measure the power spectrum basically. So this is our techniques to avoid this frequency flagging. So what we have done, so let's say these are the 2 frequency channel, we are doing the measurement. Instead of doing the measurement first, so basically instead of doing the correlation first at different frequencies, so basically in the power spectrum, generally you do the Fourier transform first in the frequency domain, go to the delay domain and then correlate them, and it will give you the power spectrum at that delay mode. But that is the problem, correct? That I showed this is the due to if I do the Fourier transform without any corrections. So generally people do that. You have to just some noise model, some inventing. That is one of the process to get rid of the channel flagging. But Here, this is also model-based. So in our idea in that, what we are doing, instead of doing this frequency measurement, basically the delay domain, first we correlate this frequency. So I have this frequency measurement at some number of channels. Instead of doing the Fourier transform first, we correlate the frequency. So now I have the measurement in delta nu domain. That's what we call as a frequency separations. And now after doing this frequency separation domain, I can do the Fourier transform to go to the power spectrum. So what is the advantage is that? Suppose I have some channels flagged in that measurement, but I will get another combination from which are the unflagged. So delta nu equal to 0 means even the, let's say channel 5 is flagged, I will get delta nu equal to 0 from the eight channels. Or if I take the another combinations, I can get rid of the missing frequency information. So that is the idea of the going to the frequency separation domain instead of frequency. And if we do the Fourier transform, it will give me the same quantity as I am interested in the power spectrum. So that is the advantage of the multi-frequency angular power spectrum and do the Fourier transform. So before applying to the data, we did some simulation study. So this is the simulations, some Gaussian random field with some known power law power spectrum, and this is the primary beam of the MWA. And we do the multi-frequency Fourier transform, multi-frequency power spectrum maps. And this is the model that we know, and these are the recovered power spectrum at different L, that is the angular multiples. And if we do the Fourier transform after, so this is basically the delta nu correlation first, and then do the Fourier transform. And if you see here that this method works better, much better without any modeling. So basically it is a model independent, and we can do the Fourier transform and get the power spectrum with accuracy 5%. So that is the simulation study, and we have validated. So now the next idea is that, so we have get rid of the frequency channel missing informations. Now, as I said, if we combine the different pointings as the sky passing through, if I combine the different pointing center, I can increase the signal to noise ratio. So that is the idea, the next in the deep scan observation. So we took this different pair combination of the pointing center, different part of the sky, different pointing center of the telescope, and I combine. So different curves here shows that how is the separation of the pointing center in that deep scan observation. So if we combine, let's say from here to too far away, there will be no signal correlation because the primary beam of this two pointing is too large. The separation is too large. So there will be no correlations. But if we correlate just nearby points, there will be some correlation. So this plot in the right-hand side shows the correlation as a function of the pointing center separation. So this is called the different delta piece pointing center separation. 1, 2, 3 means just the one separation. And if you see this is a large separation, 5, the signal falls. The correlation is normalized, so it falls. So that's why the different separations, so that will give you some idea that how much separation of that measurement I can restrict to increase the signal to noise ratio. So later we'll show that 3 is give a delta PC, basically the pointing center, 1, 2, 3 will give some reasonable estimate without any decoherence. So this is the plot again using the simulations. Now we have combined the different pointing centers with proper phasing. And here we show that this is just the single pointing center without any correlation of the next pointing. But if we increase the number of pointing center in the correlations, the signal to noise ratio will go up. So that is the different lines here. So how many pointings we have combined. So this is 31 to 37, 6 pointings we have combined, and the signal to noise ratio goes high using the simulations. This is just for the without any noise. So basically the cosmic variance only. So this study will show that, okay, if we combine more pointings, let's say 6 pointings, I can increase the signal to noise ratio at least 2 orders of magnitude, 2 orders by instead of just single pointing measurement. So now we have validated all the things that missing channel frequency can be get rid of by the multi-frequency angular power spectrum first. And then combining different pointing center, I can increase the signal to noise ratio. Now it's time to apply for the real MWA data. So we have validated algorithm using the simulations, and then this is the result. So the left plot shows the image of this one pointings using the MWA data, and this 140 millijansky is the RMS we got. And this is after removing the point sources from the data and sources above the 3 sigma removed. This is the power spectrum for one pointing. So what we have seen here, if you see this, there are a lot of horizontal structure because of even the multi-frequency angular power spectrum we have used to get rid of the channel missing informations, but still because of the periodic flagging pattern, we have seen some horizontal structure in the power spectrum, and that is seen in another estimators also for the MWA. So this is just a slice plot of that power spectrum for different K parallel. And these are just the simulations. So in the real data, these two are the simulations just for the comparison. So there's no such periodic flagging pattern. And we have seen that the periodic flagging pattern exactly matches the periodic flagging. So this periodic structure exactly matches with the periodic flagging pattern 1.28 megahertz in the periodic flagging in the MWA data. So this is the structure we have to present. So we are not able to use the whole K parallel, K perpendicular region to get the upper limit of the power spectrum, but this is not present in the simulations. We have tried that what is the issue of this periodic flagging pattern. Even we apply the same periodic flagging in the simulated data, it is not present. So this is plot the source, but in the real data, this is the case. So we have, this is the first study we have done that this structure is present, the periodic structure. This restricts our K parallel, K perpendicular region, and we use a small part of the K parallel, K perpendicular to get some upper limit of the power spectrum. So the left panel just shows one of the statistical quantity just to show that any systematic behavior present or not, but it is mostly this is the noise-like structure, and the histogram is quite symmetric in the both positive and negative, but there's some excess variance, so that might be our simulator. You have used our simulations to get the variance of that data, but might be this is the RMS we are calculating might be the smaller, the data have more variance compared to the simulations, so that is. And this is the power spectrum of the upper limit from that small region of the K perpendicular and K parallel. So this is quite high. So that we have tried that how this periodic flagging pattern are coming, even we are using this frequency correlation approach. So that is so now let's go back what is happening, because we are combining all this. So this is the frequency correlation matrix of all the channels. This is the frequency. And what we have seen that, so this is just the triangular plot, is a symmetric matrix. So we can just plot the triangular matrix here. And in the delta nu, so in the multi-frequency angular power spectrum delta nu separation, what we have done, we have averaged all of the delta nu equal to, let's say, 10. All the components that we have with 10 separation, average them together, and we get this signal. Similarly, we did the averaging in the last part that I have showed, and all this averaging we have done for a fixed delta nu, that is not the case for the data. Because if you see there is some pattern, it is not symmetric. So this is the plot just showing the one slice here, one horizontal slice. So different horizontal slice is plotting as a function of delta nu. And in that process that we have discussed earlier, is basically we are combining all of them up to get one delta nu values. But that is not the case because the signal is not ergodic in the function of frequency. So it depends on which frequency is coming. Even if the delta nu separation is same, but it depends on which central frequency it is coming. So signal is not ergodic in that frequency band. So we can't average all of them because there is a huge amplitude discrepancy in that measurement. That is basically the red line curve that we have used earlier. We averaged all of them off, and then we did the power spectrum. That is the present that I showed earlier. So this is the case actually happening in our data measurement. The signal is not ergodic in that frequency separations. So to get rid of that, we just did another simulations that were just to see the cause. So this two left and right is the simulation study again. So we have did a rigorous study why this periodic flagging is coming, even the delta nu separations we are using. So this is the same study of the simulation, but here it is a Gaussian random field with 20 centimeter signal, and this is the foreground. But you see, as I showed, this is the even it's the flagging, no flagging doesn't matter because of the signal is ergodic along the line of sight. But the foreground is not the case. So that's why there is some flagging pattern. We did the same thing here, both in the left and right. But because of this foreground is not ergodic along the frequency axis, there is a pattern along the frequency, this creates the problem. That is actually we have investigated using the simulations. So what was the next step? Let's remove the foreground first, then do the study. So this is the next step we have done, the smooth component filtering. Whatever the frequency structure have in our data, let's remove the first, then do the analysis that we have done. Because if signal is ergodic along the frequency, that behavior is not coming. This periodic, whatever the channel missing or this features will take care of this multi-frequency angular power spectrum analysis. So that's why we did this. Before doing all the studies, we removed the smooth component part from the data. And this is just like a one visibility grid. And this is the pattern. So this is the combination of the two effects. One is the ergodicity, not ergodic along the frequency, and there is a periodic flagging. So that's why we first fit a smooth component of the data, remove them, and then this is the after subtracting the smooth component. Now you see whatever the pattern or the structure was along the frequency, after removing the smooth component, all becomes now at the similar level. So now I can do this averaging over all the delta nu, all the frequency channels. Now I can do the averaging along the delta nu, because for a fixed delta nu, I can do all the averaging from different samples. That is, that now it doesn't matter actually which separation, the sample is coming from which separation. So I can take all the separations now depending on the bandwidth, and then I can average all of them. And this is now the final result. So what I have done here, we have removed the non-ergodic component, basically the foreground component, using some smooth foreground, fitting some smooth component, and then we did the multi-frequency, frequency correlation, and then the power spectrum. So this is the result, just comparison of the before smooth component filtering. That was the periodic horizontal pattern was there, and after removing the smooth component, you see that most of the K parallel, K perpendicular now free from this horizontal structure. So this is the huge improvement of our result. So here, this is the last result that I showed, and this is the new result after removing the foreground. Now I can use most of the K parallel, K perpendicular part of the MWA power spectrum to get the upper limit. So now we see here, this is the 400 time improvements over the last result without any smooth component filtering. So that is the improvement of the MWA. Now, as I said, now we have, so this was only for one pointing center. That means because if we combine multiple pointings, it will not help because the data is still dominated by these things. So after removing this first, the horizontal structure, we now go to the combining all the pointings. So now we have 162 pointings that I discussed earlier. This is the whole range. Now we did the multi-pointing analysis. So 162 pointings we have analyzed separately. We calculate the power spectrum, this K parallel, K perpendicular space, and then we combine all of them. So, okay, so this multi-pointing, all the pointing, first we have studied how the foreground looked like, because we have to remove the foreground using the smooth component filtering. Okay? So this is another parallel study we have done. We have removed before removing, we have started the foreground component first. So this is just the foreground angular, sorry, the galactic synchrotron emission measurement for a one pointing here, but we have done for all the pointings. 162 pointing. And this is the before point source removal. This is the after point source removal, and we apply this fitting, basically the amplitude part and then some power law part. And this is the synchrotron power spectrum we are considering, and the slope is consistent with the earlier measurement of the synchrotron. So this is just the parallel study. Before going to the 21 centimeter, we did some parallel study how the foreground amplitude and the behavior look like at the different part of the sky as a function of the drip scan. So this is the whole angular power spectrum versus CL versus L plot as a function of RA. Now we have analyzed 162 pointings of the MWA sky, and this is the whole plot. So this is the function of RA, and this is the CL DL. And if you see, this is there is a huge power is huge here, and this is the Fornex A is coming into the main lobe of the primary beam, MWA primary beam. So this is the amplitude becomes so high that we can't use this part of the sky because of the combination. So Souvik will present poster that how the selection criteria we have used to remove some of the bad pointings that is not that we can't use for the power spectrum study. So this is the same PK versus K. Now it is a 3D power spectrum, but again is a function of RA. So you see here both in this RA, because of the Fornex A, both the angular power spectrum and the power spectrum is high compared to the other region of the clean region of the sky. So there is another here, the amplitude quite large. So we have used some statistical tool to remove some of the pointings that we can't use for the next step. So this is the after, so we have found out of 162, only 22 pointings based on our selection criteria. That is, we found it's okay. We can combine of them, but most of them are greater than the noise expectation. So we have removed those pointings that are not consistent. And then we have combined these 22 pointings in the final measurement. This is the final power spectrum we got from the MWA, these observations. And you see here, this is the first one. This is the second one, the black one, that is after the only single pointing, but get rid of all the systematics. And then this is the final one that we have combined 22 pointing. So now it is a 10 times improvement at the low K after combining the 10 pointings. Yeah, so this is the great improvement that we have done for the MWA study. And this is the final result we got. So still, so Souvik will present the poster of the details. So now I will just slightly, so this is the MWA result I wanted to say, but we have the data for the UGMRT band 4 also. So we have done the same analysis for the UGMRT band 4, but there is no periodic flagging pattern here. Because of the MWA, it's a periodic flagging, but in the GMRT, there's no such periodic flagging pattern, but there are some channels that are bad we have to remove. So we have done the similar study, and then we have, this is a huge bandwidth actually, 400 megahertz bandwidth. So we have used the same technique, but as the signal is changing because of the 400 megahertz bandwidth, we have used, we have combined some of the frequencies and do the independent measurement. Like these are the different frequency, center frequency you have used to constrain the, to study the power spectrum for different, because the signal is, the bandwidth is 400 megahertz, so we can't do the measurement for in one go. So we have divided the chunk into 4 because of the sum of the frequency, center frequency is too bad because of the RFI. So we have removed some of the part in that data, and we have just concentrated 4 center frequencies that, this is the central frequency and this is the corresponding redshift to constrain the next power spectrum. So this is the image of that band 4 data. This is the 8 microjansky RMS noise of that deep. So basically, this is the deep 2 field archival data from the GMRT and band 4 and 8 microjansky we got the power spectrum. I have been this presenting poster for this study. And then we removed this 4 frequency, center frequency band, the whole, we have removed everything, the power spectrum, we have removed the smooth component filtering, do the multi-frequency power spectrum, then did the power spectrum analysis, and this is the final result of the different frequency band. And this is the power spectrum, spherical power spectrum of the combining the K parallel. And this is the final result for the 4 center frequency power spectrum. So this is still, we are doing this analysis, just the preliminary result of the band 4. So just summary, we have developed a novel estimator, the tracking tapered graded estimator for the drip scan observations. When we combine, the advantage is that we can combine multiple pointings in that to increase the signal to noise ratio. We have validated using the simulations and apply for the MWA disk span and GMRT data to get that. And we have seen that the power spectrum has improved a lot after applying these techniques. Yeah, thank you. Yeah.
Questions? Yes.
So I have a question on this ergodic assumption. So just like the GMRT, which has 400 megahertz, but for MWA, you said 25 to 30 megahertz is the delta nu.
Correct.
That is a significant period over which the signal statistics can evolve. So how do you justify averaging even over that 25 megahertz band?
But that's why the foreground thing we are just removing, that is the signal.
Which one signal can evolve over the 25 megahertz band?
Okay. So no, we are not considering this now. Actually, we're just averaging the 25 megahertz. But we have not seen how much the varies along that 35. If it is okay, no, we have not checked this. Is how the signal vary in that frequency.
Okay. Currently, you are probably noise limited, so you don't see it. But if you're averaging over that band, you may have a signal.
Correct. Yeah. So yeah, if the noise is low, then the signal may vary. Yeah. So now I think it's not. That's why you are getting the same level. Yeah. No, thank you. We'll try that. Yeah.
Hello. Yeah. All your in MWA plots, there is no noise curve. I was wondering like where the noise curve is, and when you take more data average it, is it actually going down as you expect from noise, or there are residual systematics which is hitting a floor, getting an excess variance in the power spectrum?
Okay. So the theoretical noise prediction, is it? So we are getting some higher because this is we are, for example, it's okay. Let me show you this plot. So this noise things, we just comparison with the theoretical part. So the variance we are getting is much higher compared to the theory part. So that's why this noise is too high. That we are under. So from using the theoretical estimate, whatever the noise we are estimating, this is one of the plot. The number will show. We are getting more higher. This 95%.
So that means like even if you integrate more, or even if you add more scans, that will not help, right? Because your systematic is dominated.
No, that's why you get rid of all the systematics, correct? Now we can, if we can add more data, the noise will less. What about the system? So this is the like a frequency missing, the periodic flagging pattern, all these things we have removed. Now it is mostly the noise-like, but the variance is high. So now if we combine, the noise will be less.
Yeah, so the non-ergodicity you said can also come from the bandpass correlations. So are there the gain solutions or the bandpass solutions are available for these data? So then probably you can check it there.
We have not checked the gain solutions as a function of frequency.
Yeah.
Yeah, that we
And
have.
also about the Arnab's question, probably the self noise is not there. But the
noise means?
Self noise means if you correlate the visibilities as the same baseline,
but
that noise is not present in this.
Because of the self, yeah, that is.
But the noise that is coming through the systematics will be still present. So that is what is.
So now, so the present is just this one, but if we go down, then the next systematic will pop up, correct? So we have to check. Now it's mostly behaving like a noise, but what kind of systematics present, we can check if we go even down, lower, yeah.
All right, let's thank all the speakers from the session again.